Hello, everyone, and welcome back. In the previous video, we introduced sequences, which were, you saw, really just lists of real numbers indexed by the counting numbers, 1, 2, 3, 4. And these things are infinite lists. And so what we talked about in the previous video was the notion of convergence. And one of the things that probably turned you off a little bit was that definition. And the definition had this annoying sort of epsilon notation. And you had to, we saw with a few examples, you've got to use that epsilon notation if you want to show a sequence converges. Well, luckily for you, in this video today, we're going to talk about convergent sequences and all the little tips and tricks and all of these things you can do to get around using that epsilon. So like I alluded to in the previous video, you're probably never going to have to use the epsilon notation, at least in this course, because you can use a lot of the tools and techniques and tips and tricks that we'll talk about today that will allow you to circumvent this. So let me start with the basic algebraic properties of convergent sequences. So let's list off some properties. Let's suppose that, say, AN converges to capital A and BN converges to capital B as n goes to infinity. So we have two convergent sequences, AN and BN. Well, then we have what's called the sum rule. And it tells us that if we add up these sequences pointwise, so A1 plus B1, A2 plus B2, A3 plus B3, and so on and so forth, then this just converges to the sum of the limits. So again, you probably knew this, you probably anticipated this, but it's important for us to write it down. Similarly, we have a difference rule. So you can do the same thing with differences, A1 minus B1, A2 minus B2, and so AN minus BN converges to A minus B. Same idea. So this gives us a way of really getting around doing some annoying computations, right? Because we can just basically examine the sequences AN and BN on their own, and then we can use them to build up to much more complex statements about convergent sequences. So another one, the constant multiple rule. And so this tells me that if I take, say, K times AN, this converges to K times A for any constant K. The product rule, well, it sort of does exactly what you think it does. If you multiply AN and BN pointwise, so A1 times B1, A2 times B2, A3 times B3, this sequence that you build converges to A times B. And we should emphasize that's a minus up there. And then finally, the quotient rule. The quotient rule tells us that if I take AN and I divide it by BN, assuming I could actually do that, so I'm going to have to assume BN is non-zero. Well, this is going to converge to A over B when BN and B are not equal to 0. So assuming you can actually do the division, right? So that's nothing out of the ordinary here. But let me show you the beauty of this. This now tells me that I can skip a lot of work in order to find convergence of sequences. So for example, let's work through some problems here. The first one, let's find the limit. The limit as n goes to infinity of minus 1 over n. Okay, well, this is the same as minus 1 times the sequence 1 over n. So I can use the constant multiple rule. So this becomes minus 1 times the limit as n goes to infinity of 1 over n. Now, remember in the last video, we did a lot of work. It took a little bit of work using the epsilon notation, the proper definition of convergence, to find that 1 over n goes to 0. And so now I get minus 1 times 0 which is equal to 0. And that's all because of the constant multiple rule. So if an was equal to 1 over n and k is equal to -1, then I'm just applying the constant multiple rule here. Similarly, in the previous video, I used this example right here to demonstrate convergence. Well, the way that I did it is I distributed the denominator. So I get 1 minus 1 over n here. Then I can break this up using the difference rule. So the limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over n. And now these are both limits that we computed in the previous video. The first one is a constant sequence. It converges to 1. The second is the sequence 1 over n. Again, it converges to 0. So this converges to 1 as we would expect. So you see how nice this is so far? I'm just using the two examples from the previous video over and over and over again, right? And we can keep doing this. We can keep having a lot of fun with this. So for example, let's look at 5 over n squared. The first thing is we'll use the constant multiple rule to pull out the 5. And I get 1 over n squared. But now I know 1 over n squared is 1 over n times 1 over n. So I can use the product rule. So I get 5 and then times the limit as n goes to infinity of 1 over n. And then again times the limit as n goes to infinity of 1 over n. And this gives me 5 times 0 times 0, which is equal to 5. Okay, let's do one more here. Let's do the limit as n goes to infinity of 4 minus 7 n to the power of 6 divided by n to the power of 6 plus 3. So you've probably done these types of quotients of polynomials with functions, and you remember there's a little trick that we do. We factor out the highest power of n in both cases. So in this case, this will leave me with 4 over n to the 6 minus 7, divided by 1 plus 3 over n to the 6. So I factor an n to the 6 out of every single term here. And now I can just compute the limit of each one of these terms individually and then just put them all back together using all of the rules. So for example, the limit as n goes to infinity of 4 over n to the 6, this is going to take a lot of work if you want to follow all the rules, but we can skip a lot of them. That is going to be 0, right? That's going to use the product rule just 6 times, just like we did in example 3. So you get 0. Then minus 7, because 7 is a constant, it's independent of n, divided by 1, that's a constant, it's independent of n. And same thing, 3 over n to the 6, you can use the product rule here to get that this goes to 0, which gives me a limit of 7. Minus 7. Right, so you can skip a lot of steps now. That's the beauty here, is that we don't have to use epsilon anymore. We don't have to make our lives complicated. We can, sort of use the intuition that we've been building up for a long time. But it is important to give yourself a proper definition of the things that you want to quantify. Okay, so then you are probably familiar with the squeeze theorem, sometimes called the sandwich theorem. So let me write it down. We have a version of it for sequences as well that we can use. So some people call this the sandwich theorem. I have been introduced to it as the squeeze theorem. And anybody from maybe some European countries, sometimes they call this the two policemen theorem. So it goes by a number of different names. I'll explain the two policemen thing in a moment. But let me write the statement here first. So the sandwich or squeeze theorem for sequences. So let AN, BN, and CN be sequences of real numbers such that you have an ordering. So an is less than or equal to bn, which is less than or equal to cn for all n. And if an converges to L and Cn converges to L as n goes to infinity, then Bn also converges to L. Right, so you see what's happening here, right? You have An and Cn on the outside, and they're both funneling you into the same spot. And so B is stuck somewhere in the middle, and it's getting, wedged into the same limit. Now, the reason that some people call this the two policemen theorem is that you can think of this, or the way it's explained is you have a sort of criminal who's trying to evade capture, going back and forth in between these two policemen, but the two policemen are slowly closing in and pushing you into the jail cell. And so that person who's trying to avoid capture is having less and less room to maneuver, and eventually they're being forced into the cell. So that's how you can kind of think of this, but this allows us to work with even more complicated theorems, or even more complicated sequences. So let me give you another example here. Let's look at the sequence, cosine of n divided by n. Well, this thing is going to go to 0 because cos is between -1 and 1. That's something that we already know for all n. So -1 over n is less than or equal to cos of n divided by n, which is less than or equal to 1 over n. And so the squeeze theorem tells us this thing is converging to L, this thing is converging to L, and so therefore the middle is also converging to L. And in our case, we have L is equal to 0. Sorry, I was trying to use the actual theorem just so that everybody could see it, but it would have been better if I wrote 0. Okay, let's do another one. How about 1 over 2 to the power of n? Well, we know that this thing is positive always, right? 1 over some positive number is still positive. And we also know that this is smaller than 1 over n. And so this is because n is less than or equal to 2 to the n for all n. So you just invert that inequality, you reverse the sign of the inequalities. But in this case, again, we have this is going to 0. It's a constant sequence. There's our old friend 1 over n. And so therefore, this thing is also going to 0. So maybe I can write that properly, but I like to do the little visual squeezing as well. Okay, let's do another one. Let's say -1 over n times 1 over n. So where do we think this is going to go? Well, this is going to go to 0 as well. So we have -1 over n is less than or equal to this thing that oscillates between plus and minus values. And similarly, we get +1 over n here. So the bounding is basically the same as cosine. It comes from the fact that -1 to the power of n is less than or equal to 1 and bigger than or equal to -1. And so therefore, again, just using 1 over n again, that thing goes to 0. So we're getting a lot of mileage out of the one example that we used epsilons for. And so finally, the last one, if we have a sequence, so if the absolute value of an is going to 0, then an is also going to 0. So you think of the absolute value as being the distance from 0, right? So this is saying if the distance of a sequence from 0 is going to 0, then the sequence itself has to be going to 0. And this is just because minus a to the n, the absolute value, is less than or equal to the sequence itself, which is less than or equal to the absolute value of a to the n. And left and right limits are going to 0 by our properties of convergent sequences. And so that wedges the middle piece into 0 as well. Okay, so now you can see, we've got some nice results here that are going to allow us to get most of what we need out of convergent sequences, just using like 1 over n most of the time, right? If you look at all the examples, everything really just boils down to 1 over n, like 99% of the time, at least for these ones. So let me give you another result, because maybe I can give you something with a square root in it, and then you're kind of like, it's not going to quite work anymore, Jason, right? I can't find the 1 over n. So let me give you another one of these properties that you can use, and this is called the continuous function theorem. Function theorem for sequences. So we should probably, if you're watching this video, you probably know a lot about continuous functions. So let's leverage our knowledge. We're good at calculus at this point, right? We can work with functions. We can take derivatives. We can do all kinds of fun stuff. Let's leverage that knowledge. We're good at that. Let's use it to understand sequences. So if I have a continuous function, I'm going to be able to use it to understand limits of sequences. So let's say let an be a sequence of real numbers. And then so if an converges to some limit L, and if f is a continuous function, or is continuous, let's be precise here, is continuous at L, and defined, so we'll be very technical here for a second, for all an. So you can actually evaluate f at each element of your sequence, then f of an converges to f of L. Okay, so maybe you're looking at that and thinking, I don't know how that's going to help me, right? What is this going to do for me? Well, let me show you, right? This all comes down to examples. So let me give you some example applications of this thing. How about if I asked you to find the limit as n goes to infinity of the square root of n plus 1 divided by n. Okay, so maybe we don't need such a big square root. Okay, well, if we let an equal to n plus 1 over n, which is the same as 1 plus 1 over n, this thing clearly goes to 1, right? As n goes to infinity. We know that. We can use the properties from the first piece of the lecture today. And so then let's take f of x equal to the square root of x. This thing is continuous, and it's defined as long as an is positive. So this tells me that f of an, which is equal to the sequence that I actually care about, this converges to f of 1, which in our case is going to be the square root of 1, which is just equal to 1. So therefore, the limit as n goes to infinity of the square root of n plus 1 over n is equal to 1. So now we've worked in more complicated functions into this thing, right? We've got square root functions now that we probably weren't able to deal with the previous two results that we were given. Let's take another example. This one is kind of fun. So let's look at this sequence. So we know an is equal to 1 over n converges to 0 as n goes to infinity. So then let's let f of x equal to 2 to the power of x. And so clearly, so then f of an converges to f of 0, which tells me that 2 to the power of 1 over n converges to 1. Now, this isn't particularly exciting in terms of the mathematics, but I think there is something that's kind of cool here. Because what's 2 to the power of n? This is the nth root of 2. So you take the square root of 2. Well, you take 2 to the power of 1, and then you take the square root of 2, and then you take the cubed root of 2, then you take the 4th root, and the 5th, and the 6th, and all the way up. If you keep taking higher roots of 2, you're getting closer and closer to 1. And as n goes to infinity, this sequence eventually converges to 1. I think that's kind of cool, right? You can do this on your calculator if you don't believe me. Just take higher and higher roots of 2, and you'll see that this thing eventually is going to be very, very, very close to 1. Okay, so we're talking a lot about limits. I've introduced functions into our discussion now. Now, when it comes to functions and limits together, there might be something that you remember that was very, very, very important. And it's so important that it's named after the person who came up with it, right? That's L'Hopital's rule. We've used it in this class before. We're going to use it again. And the beauty here is that we can use L'Hopital's rule in order to evaluate a number of these limits as well. So all of that knowledge that we had from calculus is carrying over. Maybe the last video sort of intimidated you, made you a little queasy, a little uncomfortable, but hopefully now I'm winning you back, because now it's sort of just turning back into calculus. Okay, let's do this. So let's say using L'Hopital's rule. Okay, so let's say suppose f of x is a function defined for all x greater than n0. So just, beyond this, beyond some point, you have this function defined, and that an is a sequence of real numbers. Again, it's always a sequence of real numbers, so I'm not going to write sequence of real numbers, such that an is equal to f of n, right? So you're describing the elements in this sequence by just evaluating the function at some integer. And this is for n greater than or equal to n0. This is just a technical piece of this. You're never going to see this probably when you're doing these problems. So don't get hung up on some of the more technical aspects. Then these limits are the same. This is equal to L whenever the limit as x goes to infinity of f of x is equal to L. Again, this was the correspondence I was trying to make in the previous video, where I was talking about, you can use a lot of your intuition about limits of continuous functions to understand sequences. And so, I wrote at the top of this using L'Hopital's rule. Technically, this doesn't actually use L'Hopital's rule, aside from the fact that typically this integral this limit on the right is found a lot of the time using L'Hopital's rule. So let me give you an example. Let me show you what I mean. So lots of examples today to really illustrate basically how we can use calculus to solve these things. So let's show that the limit as n goes to infinity of ln of n divided by n is equal to 0. Well, we can set f of x equal to ln of x divided by x. And this is defined for all, actually it's x greater than 0, but in our case, we can take n0 is equal to 1. So i.e. n0 is equal to 1. So that my sequence elements are just f evaluated at each integer. So therefore, the limit as n goes to infinity of an is equal to the limit as x goes to infinity of ln of x divided by x. And now we're in the case of an indeterminate form. Ln of x goes to infinity as x goes to infinity. So you have infinity over infinity here. You can use L'Hopital's rule. We've seen this before. I like to put a little notation telling people that I used it. That's L'(HR) for L'Hopital's rule. And in this case, I get 1 over x divided by 1, which is 0 over 1, which gives me the desired result. So life is good, right? We can use a lot of our understanding of functions in order to evaluate these things. Let me give you an even cooler one. So let's ask this. Does an equal to the sequence n plus 1 divided by n minus 1 to the n converge? And of course, if it does, we want to find out what its limit is. Well, here's what we're going to do. First thing, I don't like that exponent of n up top. So I am going to take ln here. So set first bn equal to ln of an, which is ln of, n plus 1 over n minus 1 to the power of n. And the beauty of using an ln here, a natural logarithm, is that the n comes out, that exponent. And so I have this now. And so now I can ask myself, what is the limit here? So the limit as n goes to infinity of bn, this is equal to, in our case, the limit as x goes to infinity. So we're going to use that correspondence that I just showed up top of x times ln of x plus 1 over x minus 1. And this is still in an indeterminate form. We're getting x is going to infinity. The ln term is going to 0 because you're getting ln of 1. The quotient x plus 1 over x minus 1 is converging to 1. And so you're getting 0 times infinity. That's not going to work. So I'm going to do probably a trick that you've seen before when you work with L'Hopital's rule. So I'm going to write this like this. Same function, nothing changed. Then what we will do is we will use L'Hopital's rule here. And so in this case, I'm going to get, so if you take the derivative of top and bottom, I'm going to just write it down because you're good at derivatives now, I think. This gives me minus 2 over x squared minus 1. So that's the derivative of the natural logarithm term. And minus 1 over x squared, which is the derivative of 1 over x. Okay, let me go to the next screen. Actually, before I do that, let me tell people that I use L'Hopital's rule. So I put the L'(HR) in there. Let's clean this thing up. So let me go to the next page. This gives me the limit as x goes to infinity of, so after cleaning it up, 2x squared divided by x squared minus 1. You've done this before. You know that the answer here is 2. So therefore, bn converges to 2. and bn is equal to the natural logarithm of an. So f of x equal to e to the x is continuous everywhere. And an is equal to f of bn, which implies that an converges to f of 2, which is equal to e squared. So that's pretty cool, right? We sort of went way, way down the rabbit hole. We used a lot of different pieces to this in order to find the limit of an. And so, this is a pretty common trick that you're going to see when you have a exponent that depends on n. Typically, you want to hit that with a logarithm so that you can pull that exponent down and turn everything into a multiplication. Then what you can do is you can undo that logarithm just using that second result that we gave today about continuous functions. Okay, so what I would like to close with is just give you a little list of important sequences that we're going to be working with as we go through here. Okay, so it's a little summary, and of course, we'll finish with some examples. So let's call these the important sequences. So the first one we've seen already, and this is the limit as n goes to infinity of ln of n divided by n. This is equal to 0. So this is, of course, we did this using L'Hopital's rule. It's a nice one. Okay. I'm not going to prove these. I'm going to give them to you. If you'd like to prove them, please go right ahead. You can follow a lot of the procedures that we've done today. The nth root of n, so this is the same as saying n to the power of 1 over n, kind of a weird one, while this converges to 1. So it's very similar to the nth root of 2. It's sort of the same behavior. So if you want to prove it in the same way, you can. Okay, 3. In this case, same thing, the limit as n goes to infinity, if x is a fixed value and you take the nth root, this is equal to 1 when x is bigger than 1. Sorry, when x is bigger than 0. When x is bigger than 0. The reason you need it to be bigger than 0 is because you can't take even roots of negative numbers. So it's not going to make any sense if you have negative numbers put into that. And in this case, x is a constant. It'll become clear in the next few videos why I'm using x. Same thing, if I take powers of x, then this thing is equal to 0 when x is between -1 and 1. So -1 is less than x, which is less than 1. That's alternatively, you could write this as the absolute value of x is less than 1, right? That's a sort of another way of writing intervals, is using absolute values. Okay, this is a cool one. Maybe you've seen it in another class. Sometimes business students will see this when they're doing compound interest. And you have 1 plus x over n all to the power of n. This thing gives you e to the x for any x. Okay, so if you want to prove that one, you can basically do it the same way. You're going to hit it with a logarithm. You're going to find what the logarithm converges to, and then you're going to undo it using an exponential. And then let me go to the next page here. The last one that I want to talk about is the limit as n goes to infinity of x to the n divided by n factorial. So we remember factorials. Factorials are when you take all of the numbers. So if I give you a number, I say 10, then you multiply all of the numbers from 10 all the way down to 1 together. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So it grows very, very fast, right? It grows faster than an exponential function, or as fast as an exponential function. In this case, It grows so fast that it's going to sink any powers of x. So this works for any x. So for example, you could take x equal to 100 here, and still taking rapid powers of 100 is slower than taking factorials. So that's how you should be sort of looking at this thing. And again, I know that it's probably not quite clear why I'm giving you these, other than, they're just interesting in and of themselves. But it'll become clear as we progress through. So I want you to have a little bit of faith in me. But for now, let's see how we can use these things. So let's do some examples first. So the first example is the natural logarithm of n squared over n. Well, this is, if we bring down that exponent out of the natural logarithm, this is 2 times the natural logarithm of n divided by n. But now, number 1 here told us that ln of n over n goes to 0. The 2 out front, we can use the original properties that we had. Oh, sorry, this is converges. We can use the constant multiple rule to see that this thing goes to 0 as well. Okay, how about another one? The nth root of n squared. This is equal to n to the power of 2 over n. So if you write that just in terms of exponents, which is equal to n to the power of 1 over n all squared. Again, just using some exponent properties. But the function that squares you is, again, a continuous function. So this converges to the limit of n to the power of 1 over n all squared. So 1 squared, which is equal to 1. Right, so think about how simple we started with. We started with just 1 over n. That was the last video, the 1 over n in constant sequences. Look where we're working now, right? We're working on nth root of n squared. And it was just by building up these little properties. And basically, we haven't seen an epsilon this entire video. So, praise be to that, right? We don't have to work with that. Now we're in a sort of general calculus realm. Okay. So how about this right here? Well, again, we can break this up into its exponents and we get this thing. And so now we can use what was our interesting limits, number 2 and number 3. And so we see that both of these things converge to 1. So I get 1 times 1, which is equal to 1. Okay, so we're having a little bit of fun. Let's keep going with it. Let's do minus 1/2 to the power of n. Well, in this case, we're using formula 4 with x equal to minus 1/2. And so we know this thing goes to 0. Okay, let's take a look at another one here. N minus 2 over n to the power of n. In this case, you can actually distribute out that denominator. You get 1 minus 2 over n to the n. And now this is formula number 5. Let's take a look at it. Formula 5 with x equal to minus 2. And so you can see that this thing converges to e to the minus 2 using that formula. Again, if you want to prove it, you can just use the same trick that we used for a previous example. You take ln of the sequence, you find out what that converges to, then raise everything to the e. Okay, last one. 100 to the power of n. So this is the example that I gave you orally, but in this case, this converges to 0 from property 6 with x equal to 100. So that's kind of cool, right? You put that into your calculator, it probably doesn't look like it's going to converge for the first, I don't know, 10 elements of the sequence, but very, very quickly, that thing is going down to 0. Okay, so what have we seen today? We have seen all kinds of wonderful, wonderful properties of convergent sequences. They are so wonderful, in fact, that we didn't see a single epsilon today. And so, we're sort of back into a realm where I think we probably feel a little more comfortable because things have kind of turned back into calculus. We're using functions again, but we're doing it in the service of trying to understand sequences. As I said at the beginning of the previous video, sequences are going to be used to look at infinite sums. Infinite sums are going to be used to look at new forms of functions. So we're really developing a huge narrative arc over the next number of videos here, and we need to sort of slowly build up our intuition. And so what we've been doing the past 2 videos, what we'll continue in the next video, is understanding first sequences until we master that.